Hello, I'm Dr. Vikramarachi again, and in this video, I will explain the theory behind Lab 8, refraction of light, and also I will explain some calculations that you might need in order to complete the lab report. Well, I believe you have learned about refraction of light in the class. So in these two pictures, especially in this one, you can clearly see the refraction effect happening in the natural world. So if you put a straw, let's say, or a pencil into a water cup, you will be seeing like the pencil is broken here, right? So that's happened due to the refraction of light. This picture is really interesting. So this wooden log is showing us two pictures over here. So this is due to the reflection of light, and this happens due to the refraction of light. So it's really, the log is like straight down, but when we're seeing it from over the water, we see it's like kind of bended, right? So this is due to the refraction. Well, so what happened to light rays when they encounter a transparent object such as glass or water? So in this picture, you can see a light ray. So as you know, the light rays can be, we are representing using arrows. So arrow is represent the direction as well. So the light over here in this picture travels straight down and entering into a second medium, right? So let's say the first medium is air, and let's say it's entering into either glass or water. So it's, you know, like it's dense material, right? So the speed of light in glass or water is less than the speed of light in air or in vacuum. Sorry, it's vacuum. So the distance between wave fronts, basically that's the wavelength, will be shorter in the dense material. So you can see it in this picture, the length, the distance between the wavefronts over here is longer than the distance between the wavefronts over there. So the, as I mentioned, the wavelength will be shorter in glass or water compared to the air. So the index of refraction is the ratio of the speed of light in vacuum and the speed of light in that substance. So here, if you're using the air as the first material and the glass as the second material, then the refractive index of glass can be calculated using this equation. So refractive index of glass is equal to speed of light in vacuum divided by the speed of light in glass. So if you know the refractive index of glass, and if you know the light speed in vacuum, then you can even calculate the speed of light in glass, right? So if you know two things, then you can calculate the other unknown using this equation. So the refractive index is depend on the material. So for vacuum, it's about 1. And in air, it's 1.000277. So as you see, it's somewhat very close, right? So it's okay to say the index of refraction for air is 1. And for water, the refractive index is 1.33. In ice, it will be 1.31. For glass, it's about 1.5. And for diamond, it's 2.417. So you see, diamond does have a higher refractive index than other materials. So that's give the quality of the diamond, and that's why it is really expensive. Well, as you know, the refraction of light also following a rule, right? So that's the Snell's law. So when the light passes from one transparent material to the other, the rays are bent toward the surface normal if the speed of light is smaller in the second medium, and away from the surface normal if the speed of light is greater, right? Well, so what did I mention there? So let's look at this picture. So here's the normal to the light. So what is the normal? Here's the border between the air and the glass. And here's the point where the light incident on. So if you draw a line that perpendicular to the border at the point of interaction, then we call this as the normal. And let's say this is the incident beam. So when you're sending the light along that line, it should go straight if we doesn't have a different material here, right? But it's bended this way in this real case because we have a second material over here which is denser than the first material. So as you see here, the light get bended towards the normal, right? So if we have a lighter material than the first material over here, then the beam will bend it away from the normal. All right, so what's the rule? The rule is the Snell's law. So here, the refractive index of the first material times the sine value of the incident angle. Again, you are measuring the incident angle from the normal. So here's the normal, and you measure the angle to the incident beam, like this one. So this angle is the theta 1. Remember, you are not measuring from the surface, you are measuring the angle from the normal. Okay, and then the product between these two, and also remember, this is not just the angle, it is sine value of the angle. And remember, when you are using your calculator, keep it in degree mode, not in the radian mode. And you are not just using the angle either, you need to take the sine value of the angle times it by the refractive index of the first medium. That's equal to the refractive index of the second medium times the sine value of the refracted angle. So this angle over here is the refracted angle. So basically you are measuring the angle between the normal and the refracted beam, right? Okay, so how can we calculate an unknown refractive index? So let's say we are incidenting a light onto a second medium, and let's say this is AR and the light is entering into glass. So this angle over here, we call this as the incident angle, and the angle over here between the normal and the reflected beam is called the refractive angle. And as you see here, a little bit of light, a little portion is also reflecting, right? So this part is the reflection of light, and in this lab we are not interested in that reflection part, but we are really interested on this refraction, which is going into the glass, right? So here's the Snell's law, and okay, so that's the path of light, but we are interested in this red color path, as I mentioned. So let's apply the equation here. So the N1, that's the refractive index of AR, because that's my first medium here, and sine value of the incident angle is equal to the refractive index of second medium, which is in glass times the sine value of this angle, the refractive angle. Now I want to solve for NG, that means I need to get rid of this sine theta R. So what I do is I'm dividing both sides of the equation by sine theta R, so I can get rid of this sine theta R from the left side of the equation. And then I left only with the refractive index of glass on the left side of the equation, and that's equal to the refractive index of AR times the sine value of the incident angle divided by sine value of the refraction angle. So using this equation, you can calculate the refractive index of glass. So in the lab report, you have to calculate the refractive index of glass using different incident angles. So basically, you're going to change this incident angle and measure the respective refraction angle, and then you calculate the refractive index of glass using this equation. All right, now there's another interesting, very interesting phenomena that's happening in light when it's refracting. So let me take you to the simulator, and then we'll come back to the PowerPoint slides and see like what it is. So here, so in the simulator, you see a picture like this one. So you have your protractor that you can measure the angles, and also if you like, we can measure the intensity as well. And let's say my first medium, I mean the light, that incident medium is glass, and let's make the second medium to be air. So basically the light rays are incident from a denser material and entering into a lighter material, right? So as you see here, the incident angle is about 30 degrees, but the refraction angle is little more than 45 degrees, right? About 48 degrees. So as you see, it's bended away from the normal because the light is entering into a lighter material. Well, let's increase this angle. And also you can see a reflection beam here as well. So the refraction is about 90% and the reflection is about 10%. Now, let's increase this angle and let's closely watch it. All right, so until that point, it's refracting, right? So here the refraction beam and here's the reflection beam. So the intensity of reflection is getting bigger and bigger when I'm increasing this incident angle. So there's a one point that it's totally reflecting into the same material here, right? So this is this scenario is called the internal reflection, because the most part, 100% of the light get reflected back into the same medium over here into the glass. Okay, so here there's a critical point there, right? So that's a critical point. So we call this as the critical angle of reflection. All right, so however, there's a critical point, as I mentioned. So just before that critical angle, there should be a one point that the light is traveling along this surface, right? So at that point, the refraction angle is 90 degrees because this light will go along the surface of where it separates the glass and air. Okay, so let me go back to the PowerPoint slide, then we can go over the calculation. So here, as you see, incident ray and the reflected rays are in the glass medium, and there's some refracted rays as well. So here, when you have the angle, like a smaller angle of incident than the critical angle, a good portion of light gets refracted. Now here at the critical angle, we see the incident beam coming in the glass, and then it's go along the surface of the surface between the water and glass. So here the refracted angle is 90 degrees, right? So that's where the point that we can calculate the critical angle, because over here it is total internal reflection. So the Snell's law is not valid over here, but Snell's law is still valid over here between this incident ray and the refracted ray, right? So let's catch this point and then we'll calculate the critical angle. I know using the simulator you can measure it, but let's practice our algebra to calculate this angle. So as I show here, let me go step by step. So here's the Snell's law. So that's where we start. That's the first equation given on the theory in the lab manual. So here N1, the first medium, that's glass. So Ng, the refractive index of glass, times the sine value of the incident angle. So as we are using this equation over to this scenario, the incident angle is the critical angle, right? So that's theta c. So Ng times sine theta c is equal to the second medium refractive index or index of refraction, which is Na, air, right? That's going to be 1, and sine of refraction angle, which is 90 degree. So nice thing about that 90 degree is sine 90 going to be 1. I'm not going to rush myself to plug the numbers here. I'll keep the notations, symbols still. So here, my goal is to calculate the critical angle, right? So I'm looking for an answer for theta z. So what I want to do is I want to keep only theta c on one side of the equation. So what I'm going to do is I'm going to divide both sides of the equation by refractive index of glass. So that Ng will cancel with this Ng. So I've left behind sine theta c only on the left side of the equation. And then I can solve for theta c. So theta c will be inverse sine of Ng, the refractive index of glass, times sine 90 divided by the refractive index of air. So sine 90 going to be 1, and the refractive index of air is 1, right? And refractive index of glass is about 1.5, but you can use whatever the number that you got by your calculations. Then you get the inverse sine of that number. Remember, it is not sine value of that number, but the inverse sine of this calculation. That way you can calculate the critical angle for air the glass to air refraction. Okay, so this internal reflection to happen, the incident beam should be incident from the denser material. So if there's like fish can see the surface better because they somehow they know their critical angle, so they can see the total internal reflection. All right, now let's look at diamond. So I mentioned about diamond at one point, right? So the diamond does have a higher internal diamond does have a high index of refraction. So that means the critical angle is small. So the light cannot easily escape from diamond because the critical angle with air for diamond is so small. So most of the light that enter into the diamond will get internally reflected. So it's not escaping from the diamonds. Like if you think about a regular glass, the light that enter will get refracted, right? So it's not that shiny. But when you think about a diamond, the light that enter into the diamond, good portion is get internally reflected. So that's give that a sparkly brightness to the diamond. So that's why it's really valuable. So refractive index is really interesting factor in materials. Well, I hope this video will help you to answer the lab report and understand the theory. If you still have questions, you may meet a TA in a Zoom meeting as we listed on the blackboard. And also you may email your TA if you have questions. If you are facing any technical difficulties, please email me. All right, thank you. And I'll see you in the next lab.